All right, guys, so we're going to talk about normal distribution here. The learning outcomes that we're going to check out or understanding a normal distribution or Gaussian distribution, as it's known. We're going to calculate probability through z-scores, and the goal of this is to harness the power of the Gaussian distribution to apply it to your job, your realm, and improve your organization through probability. Now, what is a normal distribution? We'll talk about understanding standard deviation. And lastly, we'll use z-score to determine the p-value, right? Let's go over a little bit of history. The concept of the bell curve, also known as normal distribution curve, was developed by Carl Friedrich Gauss, a German mathematician and scientist in the early 19th century. Gauss worked in the field of statistics and probability theory and laid the foundation for what we know as the bell curve today. His analysis and formation of the curve was relatively astronomical data, and it helped them understand error measurement. The term bell curve comes from the shape of the graph of a normal distribution, which resembles a bell. While Gaussian was instrumental in the development of the mathematical foundation of it, it's important to note that many statisticians and mathematicians over the years have contributed to the theory and application of normal distribution. In the Six Sigma portion of this, we talk a lot about different people that contribute to statistics over the years. But this guy set the stage for how we know normal distribution. So the Gaussian distribution, I'm going to try to just refer to it as a normal distribution, is a statistical tool that helps us understand better probabilities, right? How do we improve processes? What's the percentage we're going to hit that mark? What's the percentage we're going to hit that target every time? Now, a normal distribution, there's two concepts I want you to take note of. You have central tendency, and in a normal distribution, most of the data points are clustered around the mean, or as we know it as the average. And the furthest the data point is from the mean, the less frequent it becomes. The standard deviation measures the spread of the number in the data set. So we call this a empirical rule. So if we look over to the right, the standard deviation measures the spread of data in a data set. For a normal distribution, about 68%, 95%, and 99.7% of that data fall within one standard deviation. To look at this and say 68, 95, and 99.7, right? Now, the central limit theorem, CLT, states that as you collect more data, the distribution is centered on the average. The empirical rule is a statistical guide for us understanding the distribution of data points in a normal distribution. It summarizes how data is spread around the mean in a data set. Now, for 68% of the data, you're going to fall within one standard deviation. 95% of the data, you're going to fall within two standard deviation. And 99.7, you're going to fall within three standard deviation. This almost encompasses all of the observations in the normal distribution. So we all had this at some point in our lives, getting our weight measured, our height measured. So you can reference that on the bottom there as 68, right? Now, as you can see, this is where I was going with it. About 68% of your data fall within one standard deviation. I went ahead and made it simplistic for you and broke it up mathematically in each section for you. Within two standard deviations, you have 95% of your data. And within three standard deviations, you have 99.7% of the data, right? So as we're looking at this, I want you to think about this from the perspective of heights, right? As you're collecting, data for, your distribution or your data set, keep in mind how the normal distribution can play a role in helping you improve. So as you can see, that 68, it got replaced with mu, right? So what that does is if we essentially look at it, it turns that raw data into an understandable score, right? So the average 68, we can translate that over if we said, okay, here's the average. All right, here's the sigma value. So that's, the space in between as we discussed, right? That space in between, that lets you know where your probability lies. So what I want you guys to do is I want you guys to pause the video and I want you to draw out this normal distribution. Include the percentages, the mu minus sigma values, and the arrows up top as your tolerance levels throughout the distribution. So go ahead and pause the video now. I get asked this, how is a normal distribution formed? Well, let's say you order a pizza, right? That delivery driver's pulled over, he's cruising, right? You have the police officer who, collects a reference of data throughout his shift, right? He uses tick marks, nothing fancy, right? But these tick marks represent the speeds that he clocked people at. So you put a lot of tick marks together, you get a tally sheet, right? And in this tally sheet, you can put up the frequencies of everything below, right? So you have 50 miles an hour to 51 miles an hour to 52, all the way down to 65 miles an hour, right? This is his frequency of his patrol, right? This is what he did and how many people he either pulled over or the people he clocked going the speed limit, right? So as you can see, when we look at this, it starts to kind of form a similar shape that we know. And we call a normal distribution a bell-shaped curve. So Dr. Walter Shewhart in the 1900s worked at Bell Laboratories, and he was very big on statistical control processes. So the normal distribution helped him understand the data that he was collecting and how it formed around the mean. Now, fun fact about a normal distribution. The mean, median, and mode are all the same numbers. Because if you think about it, I can fold this normal distribution on its center point, right? And then it's going to be symmetrical on each side. You have the mean, median, and mode. The means, that's going to be the average of the data set. The median's going to divide that data set into two barriers. And the mode is going to be the most represented number in that population. So you can see in a normal distribution, it's all the same number. Now, a normal distribution, you can also consider this a frequency distribution. The averages tend to be very frequent and measures away from the mean are less frequent. Now, when you look at this, you need a minimum of 30 data points to create a normal distribution. And the reason being is if you look at this example here, as you start weighing the heights of bunnies or weights of bunnies, however you want to look at the data, the average of the samples have approximately a normal distribution. But the bigger your sample size gets, as you look in the background, the more distinct that average is going to become. You know, basically at the end of the day, as you collect more data, you can really define what your average or your baseline is. So the central limit theorem uses multiple repetitions of sample data to approximate the population's mean. So as you can see here in this photo, very similarly to the bunnies, as we're looking at this, the bunnies are going to increase in number set, and that average is going to be distinctively known. And if you think about it, if you only grabbed like a sample size of 5, right, and you have 100 random samples, that could be a biased sample. It could have been a clustered sample where it's all just in one end. So that's why we use multiple repetitions of data to understand the population mean. So, in summary, as a sample size increases, the distribution tends to behave normal. So if you guys like this content, I just want to ask you guys, if you can do me a favor, subscribe at the bottom. I started this endeavor in making education affordable and accessible. And over the last several years, I've helped almost 75,000 professionals around the world enter the career field. A lot of that has been based on free educational programs designed to help people get into their career. So if you could please do me a favor, share this YouTube page. That would be great. Subscribe at the bottom, but let's kick it back off with Z-scores. Z-scores calculate probability through understanding what your data set is, right? So if you look at that distribution, Z-scores are going to help us understand what probability or the likelihood we'll hit the target, right? When you ask yourself, what's the probability? Well, if I flip a coin, I have 50% of the chance of it landing on heads and 50% chance of it landing on tails. If I look at the dice, for example, depending on what one die lands on, you have a 1 out of 6 chance. So the other die is going to be 1 out of 6 chance as well. So as you start looking at this, probability is the probability we're going to hit the target, right? When I look at percentage yield, right, that's kind of the same thing, right? When I look at my process yields a certain percentage, that p-value represents that yield, right? So you're finding it through the data. So if we look at a probability, but there's 52 cards in a deck, one or 6 sides to a die. Probability is like a way to guess how likely something is going to happen. You calculate it by dividing how many good outcomes you want by all the possible outcomes. There's 6 sides to the dice. So let's look at an example here. What is the probability of rolling a 3 on any given roll? Well, it would be essentially 1 out of 6, or 16.67%. I get asked, Zach, in education format, how many decimal points do I use? And Really, I try to look at it like this. Think about the data you're working with. If you're working with bigger measurements, those minute little values are not going to matter as much. I usually say go up to 2 decimal points, and that's going to get you a ballpark where you need to be. So, what is the probability of rolling a 3 on any given dice? Well, it's 1 out of 6. What is the probability of getting a 6 when rolling a 6-sided dice 3 times in a row and getting a 6 each time? Well, essentially, you would have that same probability going through 1 out of 6, 1 out of 6, 1 out of 6. Multiply that together, and then you would have your probability. I displayed it as a fraction, but that's as simple as just putting it into a percentage format. So let's look at another example here. When we think of probability, you can use this on a various different data, right? Well, if you have 10 red marbles and 5 blue marbles, what's the probability of randomly selecting a red marble? Well, there are 10 red marbles in the bag. There are a total of 10 red marbles plus 5 blue marbles. So that's 15. So the opportunity is 15. So essentially, it's the number of red marbles divided by the total number of marbles. That's going to be 10 divided by 15, which is 2/3. And then you can move it into a probability fraction or percentage by then. On example 3, you have deck of cards, right? If you draw one card from a standard deck of 52 playing cards, what's the probability of getting a heart? Well, the number of hearts is the number of cards. So in this case, the probability would be with 13 ace or heart covered cards divided by 52 cards out of all. When you simplify that, you get about 25%. Now, when you determine your sample size, a key in research and survey design, factors affecting the sample size, population size, or margin of error, the confidence level, and variability. In this session, we're only going to talk about normal distribution. And the later on videos, if you're still a part of the same course, we'll go through and discuss these variables. This is typically when we talk about these things, I bring this into our Lean Six Sigma Black Belt program because that's where you need to know a lot about those statistical values to be able to understand those confidence levels, those variabilities in your industry. So now we get on to the Z-score area, right? Z equals X minus mu divided by sigma. Z-scores help us understand data at a glance, right? If we look at, our credit score, it's standardized. If you look at a test, it's a standardized test. It's a standardized test. So when we look at this, right, that standardization is essentially bringing that raw data that you're collecting and bringing it to a standardized test so you can understand where your performance is at. So in this case study, we're going to look at delivery times with Z-scores. So I have this case study here. I want you guys to take a little bit look over. If you look over to the left, right, the text and shapes are going to be what the datas are, right? We talk about X minus mu divided by sigma, right? X is going to represent your observed value. Average or mu is going to be represented by that symbol. And your sigma or standard deviation of a sample is going to be represented by that, along with Z-score, of course. So in this scenario, say hello to Chad over there on the right. Chad delivers pizzas for us. Not the sharpest tool in the shed, but he gets the job done. Here's the scenario here. A pizza delivery driver delivers pizzas. Yeah, I think that's pretty obvious, Zach. The average delivery time in that shop is 20 minutes to deliver a pizza, with a standard deviation or sigma value of 2 minutes. Chad delivers his pizzas a little bit later in 20 minutes. Based off of this information, I want you to calculate what the z-score is. So go ahead and pause the video now and work this calculation. If you see up at the upper left-hand side, I've included all of the values for you to use. So plug and play and stop there and continue the video. All right, pretty easy, right? You're just putting together the math and just kind of working through it algebraically. Now, when we look at this, right, we look over to the right, I've provided the solution for it. Well, we knew Chad's delivery time was 24 minutes. Well, we knew the average was 20 minutes. So right there, you know we're looking at the left side of the curve because that's going to be the lesser metrics. And then we're going to divide that by 2. So we'll get 4 over 2, which is going to equal 2. Well, what do I do now? Well, this is where we have something called a probability table. Now, this probability table, as you look at it, this is called a normal curve table A, right? So if you look very closely at this curve, we're only looking at 1/2 of it. Remember, your normal distribution altogether is 100% of the data, right? So go ahead and right away subtract 50%. Okay? So that's what this table is looking at. Now, if we were looking at the negative values, it would be the other half of the curve. So let's look at this example. We have z equals 2. That's what we calculated with Chad's delivery time. So if we look at the chart, what's the likelihood of us hitting this target region right here? Well, that's where the p-value really comes in play, right? We have to bring value to our organization and looking at processes. So that probability he's going to hit that target range the next time he goes out, well, of course, we want to collect more data. We probably wouldn't want to go off of one data point. But, you could get one data point and have 30 of those data points and then do you could put together a normal distribution off of that. And that's the purpose here, to see the target range of where he's going to lie next time he goes out. So when we look at a z-score of 2, I don't know what the probability is here. I see z-scores here, but I want to show you how to read this. This is not hard at all. And after this, I'm going to show you a super cool way of doing this. So stay tuned. So when you look at this, right, we have a z-score going down and we find 2.0. And then if you look over to the top of that chart, you see how you have to look over to the right. So like, for example, we're looking for 2.0 go down, and then you see 0.00. And then we would match those values together to get 0.4772. Now remember, that's only half of the distribution. Well, what do I got to do here? Well, I've got to add the other 50 to it, the other 50%, right? So as you're looking at it, the reason we did that is that chart says 0 to z, right? That's exactly what we found. But that's not the probability as a whole. That's just that one likelihood. So we're trying to look at this as a way to equate the p-value. So when I add it together, I get around a 97%, 0.9772%. So it's the likelihood of you being within that range. Just remember, each side represents 50% of the data at the average point, right? So as you're looking at the negative z values, they're going to be to the left. And as you're looking to the right, That's going to be the 50% positive z-values. I think we can look at it from a different perspective. Let's look at blood pressure at a hospital, right? I've got Nurse Kathy here, and Nurse Kathy measures a blood measure of the average blood of the patients, right? And it's at 120 beats per minute, or however they judge it, right? And they have a sigma value or a standard deviation amongst her patients of 15. That means that, within that, there's could be a lot of variation of 15 over, 15 under. So Kathy measures a patient with a blood pressure of 105. I want you to calculate the z-score here. So Nurse Kathy measures the blood pressure. And as you can see, when you calculate it, you get a z-score of 1. Well, again, we have to look at the z-score here. What's the likelihood of us hitting that target region? Well, that's when we look at it and just go 1 down and over to the right, add 50%, and we get 84%. In summary, the fundamentals of a normal distribution, we explore the basic characteristics of a normal distribution, focusing on symmetry and around the mean and spread of data as a measure by the standard deviation. We noted that in a normal distribution, most data points cluster around the mean, right? With fewer points, as you start to move away, they get a little bit less intense around the mean. We talked about visualizing a normal distribution with specification parameters. This helps us understand how the data is distributed in different units. And then we summarize basically the empirical rule, which data and how data is spread around the mean in a normal distribution. And according to this rule, about 68% of the data falls within one standard deviation, 95% of the data falls within 2 standard deviations, and 99.7% data lie within 3 standard deviations. Guys, thank you so much for watching this journey. I put a lot of effort into these videos, make accessible and affordable. And at the end of the day, I just really want to say thank you so much for being here and making this organization what it is today and helping others around the world. We'll see you in the next video.